Let's start today's lecture. We were doing slide set number 9, and let's continue. Let's see that what all we need to do there. Okay, so we had already covered few basic properties like properties of linearity, time shift, convolution. This is what we were doing, convolution. So convolution in time domain, we said is going to be multiplication in the frequency domain. So before I continue further, any questions on that count? Anybody having any questions here? So this property, very useful, and you will see that how it makes life simple for us once we want to find out output for certain systems. So those systems whose input and impulse response Fourier transform is quite straightforward, it will be much easier for us to directly take Fourier transform of both h of t and x of t, and then just multiply the two Fourier transforms, and those Fourier transforms multiplied would be Fourier transform of the output. And then we can just take inverse Fourier transform and find out your y of t. So another way of solving, if we know how Fourier transform of x of t and h of t exist, then just multiply those two Fourier transform and you will get your output. Now to prove that this is right, the proof, although I can do it separately also, but it is given right here. So we can see that here y of t is the output, which is convolution x of tau h of t minus tau, and if we go for the Fourier transform formula, it is basically integral of y of t e raised to the power of minus j omega t dt, and y of t we know is this whole integral right here. So what we can do is we can change the order of integration and take dt inside the tau outside, and inside here, because h of tau is constant as far as dt is concerned, we can keep it out, and inside we are left with this whole integral right here. Now this whole integral that you see right here is nothing but Fourier transform of h of t minus tau, because we know that Fourier transform is that particular thing multiplied by e raised to the power of minus j omega t dt integrated over the entire range. So this thing is nothing but Fourier transform of h of t minus tau. If h of t has Fourier transform hj omega, then h of t minus tau, the time shift property, its Fourier transform would be the same hj omega multiplied by e raised to the power of minus j omega tau. This is what you're going to have. So this whole Fourier transform will end up giving you just this e raised to the power of minus j omega tau because of the time shift, complex exponentials, and hj omega d tau. Now this hj omega is basically a function of omega, nothing to do with tau, we can just take it out. And inside we are left with x of tau e raised to the power of minus j omega tau, this product integrated over the entire range. And this is nothing but your Fourier transform of x of t or xj omega. So as an end result, we saw Fourier transform of yj omega is basically product of Fourier transform of hj omega and xj omega. Or in other words, we actually showed that if we take Fourier transform on both sides, what both sides? These both sides, where on one side we have y of t, and on other side we have this x of t, Fourier convolution with, sorry for this, x of t convolution with h of t. So if you take Fourier transform on both sides, what do we end up getting? We end up getting on left side by j omega, on right hand side we end up getting this multiplied by this. So convolution got changed into multiplication. So this is how we can simply prove this thing. Okay, so this was a very simple, you can say, way of trying to prove the same thing, that convolution in frequency domain, in time domain, ends up giving us multiplication in the frequency domain. Okay, an example, a simple example here, where we are given the impulse response of the type e raised to the power of minus bt ut, input signal again of the type e raised to the power of minus at ut. So if we are given this, then if you have to find out the output y of t, then multiple ways to find that out. So the problem is straightforward, that we have to find the output y of t, and we are given all these things. We are given x of t and we are given h of t. Now one way of finding output is simply taking the convolution. We can do convolution of x of t with your h of t, convolve with h of t. But here that convolution will end up giving you that integration formula. So if you want to use your recent knowledge of this Fourier transform, then how do we do it? Now this e raised to the power of minus at ut, a very common signal, and I told you we will be coming across this signal again a lot. So Fourier transform of this thing is simply this 1 over a plus j omega. And similarly, e raised to the power of minus bt ut, very similar signal. Its Fourier transform is 1 over b plus j omega. So these two Fourier transform we know. Then to find out output Fourier transform would be just multiplication of these two Fourier transform, just like 1 over b plus j omega into a plus j omega, simply this. Now to find the inverse, although we can use the inverse formula, but that inverse formula involves your integration. And again, engineers typically tend to go for a simplified version of things, that how we can simplify the whole thing. Sorry, y j omega e raised to the power of j omega t d omega. So although we can use this formula to find out yt, but typically what we do is we just first of all express this y j omega in a simplified shape of the type a over a plus j omega plus b over b plus j omega. Then we can simply find out the result. So this thing, you already know what this thing is. This is basically expressing this whole term in terms of partial fractions and finding out these constant a and b. Remember, these b and a are supposed to be some constants. It can be 1, 2, 3, whatever. So if we are given this type of a situation and we have to find inverse, we tend to first express them as partial fractions, and then we can directly find out the result. Then we know that inverse of this thing will be a can be kept separate. 1 over a plus j omega is e raised to the power of minus at ut. And again, b can be separated, and we have 1 over b plus j omega, which will be inverse would be e raised to the power of minus bt ut. So we can directly write the answer. And if you do this partial fraction, you will see that your a and b can be computed. If these values are given for a and b, we can write those values. If not, then we can find, and you will notice that a will come out to be 1 over b minus a, and b will come out to be equal to minus 1 over b minus a. So these are the constants that we come across, and we can just take 1 over b minus a common outside, and inside we can express this as this minus this, and inverse would be directly written here, constant outside, and this inverse would be e raised power of minus at ut, and this inverse will be e raised power of minus b t ut. So quite straightforward. So this is actually showing you an example where we see that how just using this property of Fourier, we can easily find out output. And you will see that especially once we have these complex type of systems. Just give me a minute. Okay, so this is again showing you how we can simplify the whole, you can say, finding output for comparatively more complicated type of systems. Now this is something which you will be using later on, sort of heads up. This is something you will do a lot in your DSP and later higher on courses. But because we have done this Fourier, some basic information is already with us. So here, this is basically showing you that how a simple low-pass filter is actually designed by engineers. So for this, I have to again go for a blank page and try to give you a sense of it. Okay. So what we had seen earlier was so this is the scenario that we have for a continuous time, and again this is what we have covered so far, that if we are given a continuous time system, input x of t, output y of t, and the impulse response is h of t, then if you want to find out output, one way is we do convolution. The other way we just now found out was that we can find out the product of Fourier transforms xj omega and hj omega, and this product will be the Fourier transform of your output y of t. And then we can take inverse Fourier transform of yj omega, and that will give us y of t. And proof of this thing, we just now saw that how this convolution ends up becoming multiplication. Once we just a few slides back prove this, that if you take Fourier on both sides, this end up becoming this and this end up becoming this particular thing. So now if you see here the output we can write it in any order. It is basically hj omega into xj omega. Now there are few simple points that you need to be aware of. First of all, if we take Fourier transform of x of t, it is xj omega. Now what does it mean? What is it giving us? We say we go from time domain to omega domain, and this xj omega, at times we refer to it as the frequency contents of x of t, or technically more correct term would be angular frequency content of x of t, because we can then plot xj omega against omega, and this omega is basically angular frequency content, and let's say xj omega is something like this. Typically you will notice that for continuous time non-periodic signal, the frequency content forms sort of a continuum. That's very typical. And real signal always end up giving you sort of even, you can say, plot of xj omega. So if you have a real signal, you will always get a even plot across this y-axis right here. This y-axis, which is omega equal to 0, represents your DC or zero frequency. And each point on this axis, I think I have talked about it earlier also, actually refer to a complex exponential. For example, if we take any point right here, which is omega 1, and we see the value for that, and that comes out to be, let's say, some value a. Now what is this showing us? This is actually showing us the value for complex exponent e raised to power of j omega 1t, and this complex exponent has, or complex frequency has value equal to A. And because it is supposed to be even for real signal, you will notice that for minus omega 1 also you will have sort of a equal value. Now these two together, if you add them together, they end up giving you your value of cosine, a real frequency or frequency of omega 1. So this is something which it is very important that you understand right now, that how do we see this plot of xj omega. I told you that xj omega is sort of equivalent of the coefficients that we have for complex exponents. And if you plot xj omega against omega, the plot that you are seeing, we say that this is a plot showing us the distribution of frequencies or frequency contents. But more technically correct is that it is showing us angular frequency content. But angular frequency content are related to actual frequency by a factor of 2 pi. And we know this, we have talked about it earlier also. So this xj omega is basically your angular frequency content or frequency content of your signal x of t. Okay, so similarly, yj omega is supposed to be angular frequency content or frequency content of your output y of t. Now once these frequency content go inside a system, the output that you get is something which is yj omega or frequency content of the output. So what actually happens? See this equation right here. The input frequency content gets multiplied by hj omega. And what is hj omega? We have multiple names with which we engineers refer to hj omega. One, we know that it is basically Fourier of h of t. This is one name, but more commonly we engineers refer to this as, this is interesting, frequency response. We call this as frequency response of a system. So hj omega, we refer to this as frequency response of the system, although it is just Fourier of h of t. But why do we call it as frequency response? Because whatever input frequency contents are coming in, this hj omega shapes those frequency contents or gets multiplied by those frequency content to give you your output frequency content. Now let's take this example which we are going to talk about on the slide set. If we have hj omega already given to us as something like this, minus omega c, and 1. If this is your hj omega, then this is something which will get multiplied by your xj omega to give you your output. Now notice this. This hj omega value is 0. Its value is, let me write it here, hj omega, the value is 0 for omega greater than omega c, and the value is 1 for value of omega less than omega c. So omega c is basically, we can call it a cutoff frequency. So all the frequencies which are beyond this omega c will get eliminated because they will get multiplied by 0, because we are multiplying hj omega with xj omega. And the end result that we will have would be something like this. So from minus omega c to omega c, all the contents that we have, that will remain. Let's say this amplitude was b, so this will remain b. So all the frequencies which are between dc and omega c, they will pass through this system as such, and all the frequencies which were beyond this, they will get eliminated. So all these frequencies got eliminated. So this that you see right here is an ideal low pass filter, because it is filtering out or cancelling out all the high frequencies and letting the lower frequencies pass through without changing it at all. So this is what this thing is doing. You can see it right here also. The output frequency contents in case of a low pass filter, you will notice that its frequency response of low pass filter is something like this. And what this does is this actually cancels out all the high frequencies and allows the lower frequencies to pass through as such without changing it. So output frequency contents are input frequency contents multiplied by hg omega. And we call this hg omega as the frequency response of the system, because this is how it is going to respond to different frequencies. So a very important thing, and again here we are just sort of introducing this, but you will be covering this in detail in your DSP, where you'll be designing these types of filters yourself. Now, designing is what? Designing is basically coming up with the value for impulse response. And again, if you want to come up with value of impulse response, if you know hg omega, h of t would be 1 over 2 pi inverse Fourier transform of this minus infinity to infinity hg omega e raised to power of j omega t d omega. It will be simply this. And if we just see this hg omega, its value is 0 all the way from minus infinity to omega c, and again 0 from omega c to all the way to infinity. It has value 1 just between, it has value equal to 1, this thing has value equal to 1 just in between minus omega c to omega c. This value is 1 e raised to power of j omega t d omega, and we can just plug in the value and do integral plug in the value, and this would be e j omega t integration will give you the same thing divided by jt. We are integrating with respect to omega minus omega c to omega c. Now jt is constant, we can just take it out, or we can just have this 1 over pi t into 2j into, we will have this e raised to power of j omega ct minus e raised to power of minus j omega ct. And this 2j, if you take inside, it becomes sine. So we end up getting simply sine omega ct over pi t. So what we end up getting is basically a sink. This is a sink. Sine some constant to theta divided by some constant to theta. So it will be basically a sink. So this is your h of t. So let's just go to your slide set and see what all was covered right there. All these things are already on your slide set, but I was just explaining it here also. So if you see here, all those things are given right here also. So we were talking about designing of a low pass filter. First of all, why and how we call this thing, as a low pass filter, that I explained. Because this hj omega, we refer to this as frequency response also. And this is also Fourier transform of impulse response, or Fourier transform of HOT. But typically, especially in DSP and courses after DSP, you will always be referring to this as frequency response of the system. So if this is frequency response, then what is the impulse response? We can find out the impulse response. Now typically once we say we have to design a filter, that means we have to come up with an equation for impulse response of a filter. So in frequency domain, this is how a low pass filter should look like. It should cancel out all the frequencies beyond omega c and allow all the frequencies from 0 to omega c to pass through as such without any modification. So we actually took inverse Fourier transform of this thing, hg omega inverse Fourier transform. We applied the formula and end up getting sine omega ct over pi t. You can plot this and you will see that it ends up being a sink. So So depending on what value of omega c you are selecting, you will end up getting a sink like this. This is your h of t against t. So this is the impulse response, and this is what is known as designing, coming up with the equation for this. So this is a very famous equation for a ideal low pass filter. And again, you will cover this thing in detail in DSP, and specifically the same slide also will be there. And there you will be seeing that once we have to design a filter, our interest is that we should be able to build it also. Now, this ideal low pass filter that we are seeing right here is more of a theoretical thing. We cannot really build it. Reason being, it has on T domain two-sided, it is two-sided, and that is why it is basically non-causal. If h of t is two-sided, we call it non-causal. If it is one-sided on the left-hand side, it is anti-causal. If it is one-sided on the right-hand side, we call it causal. So, being non-causal, this is something which is theoretical. So, if you want to build it, then how do we build it? That again is a topic, a whole topic for 2 or 3, you can say, lectures covered in DSP. The other thing is, again, this would be covered in DSP. In time domain, we can see these oscillations. These time domain oscillations, again, while designing any system or filter, are typically undesirable. So how do we overcome these problems? That is something you're going to cover in DSP, but it's just showing you that how does an ideal low pass filter frequency response looks like. And it is also showing you that for an ideal low pass filter, how does its impulse response looks like. So frequency response, impulse response for an ideal low pass filter, frequency response, impulse response, and the problems that are faced if you want to build it. Now, can we approximate this low pass filter with a very simple system which can be easily built? That is something which we have already covered, and I will just explain that how. Consider a system whose impulse response is of this type, whose impulse response h of t is simply e raised to the power of minus at ut. Now remember, this e raised to the power of minus at ut, if we want to plot this, it is a decaying exponent. It is a decaying exponent, and this is typically for a greater than 0. So this is the type of curve that we get. This is t. And if you notice that this curve, because of this ut element, is one-sided, that means causal, and also that this curve does not have any oscillation, it is very smoothly decaying down. So these two problems are not there. Now, to see the frequency response hj omega, we can take Fourier transform. We know Fourier transform comes out to be something like this, and we can select appropriate value of a accordingly, according to which the plot can be done. And you have seen this, that plot for that comes out to be something like this. Depending on what the value of a is, this main lobe can become thinner or wider or whatever. So this is hj omega. If we compare this with our ideal low pass filter, quite different, looks quite different. But interestingly, that in many cases can be taken as a poor man's low pass filter. We just select appropriate value of a, so that this our cutoff frequency is basically 3 dB down. So whatever is here, it is basically 3 dB down value, 1 over is 0.707, of this a. So 3 dB down value we select, and this we say is a poor man's low pass filter, because all the higher frequencies, they are being multiplied by a very small value or attenuated, and all the lower frequencies are not attenuated that much. So it actually approximates a low pass filter, and that is why this e raised to the power of minus at ut at times is good enough to act as a low pass filter and used in many different scenarios also. And again, here it is listed that why we can go for it, because it is causal, non-oscillatory, and performs a degree of low pass filtering. It is not an ideal low pass filter, but in many practical scenarios, that's good enough. So multiple things we saw here, and out of those things, the important take-home points, remember that this Hj omega, we tend to call this as frequency response of the system, because this Hj omega gets multiplied with input frequencies to give you your output frequencies. Next, an ideal low-pass filter will look something like this. In frequency response of an ideal low-pass filter will look something like this, multiplying all the higher frequencies by 0 and multiplying all the lower frequencies with 1. And we can find out the impulse response of this Hj omega, which will be h of t, which will be just inverse Fourier transform of this. So we can take inverse Fourier transform and get h of t, which is according to formula comes out to be a sink. So we end up getting a sink right here. Now this h of t, which is a sink, actually gives us two problems, a very well-known two problems for low-pass filter designing. One is that this is two-sided or non-causal. The other is that it has oscillations. These two things, why they are not very, you can say, helpful once we are trying to build a system, they will be covered in detail in your DSP course. But just take my word for it that first of all, non-causal are more of a theoretical thing. They can't be built. And oscillations are typically not desirable. Now, how to overcome these problems and come up with a good enough low-pass filter? And for that, e raised to the power of minus AT ut, if that is taken as impulse response of a system, you will see that its frequency response approximates a low-pass filter because it performs to some degree low-pass filtering. And it does not suffer from these two drawbacks. First of all, it is causal, right-hand sided. The other, it does not have any oscillations. So this is what we have for this low-pass filtering. And again, here are the summary of whatever we have covered in this slide set. We started with the properties of Fourier transform. First, very simple common property, linearity and time shift. It obeys both scaling property and additive property, and together they are known as the linearity property. We also saw time shift property, and time shift is not actually written here. Time shift property was that if x of t is xj omega, x of t minus t naught would be e raised to the power of minus j omega t naught into xj omega. This was your time shift property. Okay, next we saw differentiation and integration property. Differentiation is very commonly used, so that's written here. Integration hardly used, but again we know the property of that also. And convolution. Now this differentiation, convolution and linearity type of properties are very commonly used, and you will see that if you are comfortable with these properties, it will be very easy for you to find out output for multiple different systems or solve different situations. So this was the summary, and again all the questions related to it are also given right here. Any questions here? Any questions? So anybody having any questions on this count? Okay, so if there are no questions, let's continue. The other topic, if we continue with this thing, so coming over to this details about Fourier series and Fourier transform. Now, few things I have already covered in detail, and I'm going to repeat it here because they are important. One thing is Fourier series is for periodic, and in periodic function it repeats after time period t. Using that time period t, we can find fundamental frequencies. The periodic, you can say, function can only have fundamental frequency and its multiple. It cannot have any other frequency in between. So this is one of the important aspects that you should know. And the value of or the magnitude of each complex exponent can be found using this formula for AK, and we can plot your AK against K axis. Now this K axis is very interesting axis. It has plus minus 1, plus minus 2, things like that. Now, what are these plus minus 1, plus minus 2? These are basically representing the harmonics. 0 is actually giving you the value of DC content. So A0 is basically giving you the value of DC content. A1 and A minus 1, they are actually giving you the value of complex exponents which are conjugate of each other, or the first harmonic, as we can say. The first harmonic and its conjugate. The second harmonic is basically your A2 and its conjugate. Sorry. So together these actually give you a real frequency. Now if we somehow compare this with your omega axis, if we compare it with xj omega, this 0 corresponds to the same DC value. This 1 will correspond to your omega naught, minus 1 will correspond to minus omega naught. And the value that you get here will be different from this, and the difference will be just a scaling factor of 2 pi. So if this is A1, this will be 2 pi times A1. If this is A minus 1, this will be 2 pi times A minus 1. And same goes right here also. So it is equivalent of this thing. A very interesting thing to notice here, because this is showing you the relationship between the coefficient A and Fourier transform. So if we have any signal, let's say periodic signal x of t, we can take its Fourier transform and express it like this, or we can take its, let's say, we can take Fourier series, express it like this, or take Fourier transform, and Fourier transform will come out to be something like this. And this is something that we have seen earlier, that the relationship between your A and xj omega is basically the scaling factor of 2 pi comes in. Otherwise, they mean more or less one and the same thing. And if you have a periodic sort of a function, you would see that its Fourier transform will not be giving you a continuum, it will be giving you these sort of impulses. Any question? Any questions? Okay, so this is one relationship that we should be aware of, that what is the relationship between A and X. The other, each point that we see on this omega axis is basically a complex exponent. If you see, this side is positive side, this side is negative side. Now, what is a negative frequency? There is no such thing as a negative frequency. Once we see the positive and negative part, it is basically the positive part is one side of complex exponent, negative side is the other side or the conjugate part of complex exponents, and they together give you real frequency. If you combine these two complex exponents together, they will give you one real frequency. And this is something that, let me do a simple example right here. For example, if you are given x of t is equal to cosine omega naught t, or let me give it a value 2 pi 100. Typically we write omega in terms of 2 pi something. So omega naught, which is 2 pi 100 times t. If x of t is given like this, we can plot it. And this is Fourier. If you express it as Fourier, you will see that your AKs would be There's some things like that. It will be having a1 and a minus 1, and the value here each side will be 1 over 2 and 1 over 2. This is how it is going to come out to be. Or in other words, you will see that your x of t can be written as half e raised to power of j 2 pi 100, which is our omega naught t. This is omega naught, this is omega naught, remember, and plus half e raised to power of minus j 2 pi 100t. So instead of omega naught, I have just written a value. Don't get confused with this. Okay, so now if we, let's say, want to take its Fourier transform, you can take its Fourier transform xj omega, and you will see, although you can put the formula and do or whatever, but the end result would be you will end up getting two spikes right here, one at omega naught, the other at minus omega naught, and each having value equal to pi. So this is your omega. See the comparison right here also. A1 gets translated to omega naught value, and it will be that A1 divided by, sorry, 2 pi times A1. 2 pi times A1 will be this. 2 pi times A minus 1 would be this. So this is what it is going to look like. And if I just write it here somewhere, your xj omega, you will see that it will be pi times delta omega minus omega naught, and we can even put the value right here if you want. I was just avoiding writing values. So omega naught, although we can write a value here also, but it will be something like this. So this will be the Fourier transform. So a very interesting and you can say useful thing, which if you understand now, it is going to make your life much simpler and much easier. Okay, any further questions here? No questions? Okay, let's take about 10 minutes break and we can come back after 10 minutes. Okay, so let's start. Now, what we need to do now is basically a quiz. I will give you a quiz and I want you guys to do it by your own hand and submit scanned copy of this quiz back to me, and let's see what we can achieve here. Okay, so let me write it down right here. This is your quiz number 1. So you are given a rectangular, okay, let's take it simple. 1 second. And this value is, let's say, 1. So we are given this x of t, given x of t, which is a single pulse, and from minus 0.1 second to 0.1 second. And you have to find out the frequency content present here, part, and B part, find out magnitude of, let's see, okay, 100 Hertz frequency in this pulse. So this is a quiz which is given to you on 1/1/2021.